The following example is taken from this textbook, Thermodynamics An Engineering Approach 8 editions. Hi, okay, so we are moving to the next part of the video where we're trying to solve for this thermal cycle efficiency. So let's begins with by stating down the mathematical expressions. Okay, so for B part, right, you were asked to find the thermal cycle efficiency, where the definitions for thermal cycle is W dot net divided by your Q dot in. So if we expand these equations, it's going to be W dot of your turbine minus with W dot of your pump divided with your Q inside your boiler. And when we scroll up here, your turbine is located in between state 3 and 4, right? So the value here is actually your H3 minus your H4, and your work pump will be state 2 and 1. Okay, so this is going to be H2 minus your H1, and that you have a boiler which sits in between state 2 and 3. So this is going to be your H3 minus your H2. Okay, and if it's W dot, so you are going to have your M dot over here, but we have a bit of conflict where we need to find the M dot at the final questions. So given that this is just a ratio, so it is okay if you and at the end of the day we are going to leave it as efficiency, which is by percentage. Okay, so it is okay that we left this one as only W. Okay, and we can write it as small letter. Okay, so this is going to be your W turbine, W pump, W boiler. I would like to remind here that W dot stands for megawatt or kilowatt, or it could be in kilojoule per second. Notions with W means simply kilojoule, sorry, and the small w means kilojoule per kilogram, right, for every specific mass. Okay, so it goes the same with Q dot, Q, and the small q. Alright, so let's move to solving this thermal efficiency over here. So as you can see, you will need all this value and all the state involved. So you will need H3, H4, H2, and also your H1. Hence, in solving this, we will go through state by state. Okay, starting from your state 1, where given to you P1 is equal to 10 kilopascal. Now I'm going to bring down the I'm going to copy paste this one down here so that it will be much easier for us to have a look. And that in order for you to read your probability table, you will need two known value. So this one at the state 1, your H1 is actually equal to your HF. Right? So because you were given 10 kilopascal, so you are going to read it from table A5, where the first column, where you have the first column is your pressure. So again, I'm going to show you this in appendix 1. So you will see that the table A5 is for pressure, right? If the information given to you is temperature, so you are going to make use table A4. Okay, so moving to the next part, what you will need is another value, but I'm going to leave a little bit blank over here. So, and I will explain it later why is it so. So moving to the next part is we wanted to find the state 2. Okay, so state 2, we have the pressure is equal to 10 megapascal or 1000 kilopascal, right? And your H2, right, is actually in this compressed liquid region. Okay, so how are we going to find your H2? Now, in solving your part over here, okay, you will need to retrieve back the knowledge from open system. Okay, where open system you have 5 devices, and one of it including your pump and also your turbine. And another knowledge that regarding your pump that you need to recall back is the functions of this pump. So basically, the functions of this pump is to pump in the water that the steam that has turned out into water, to pump in into the cycle, and the cycle repeats, right? So basically, the functions of this pump is to pump in your water from condenser to your boiler. Hence, there's no heat, or maybe the most closest word is there's no significance in heat in analyzing your pump over here. So the main concern is about the flow, because when you pump in, right, obviously you are the velocity of the liquid is going to increase. And also there's another relations that you can make use is the pressure. So if you see here, the pressure 1 and pressure 2 is different. So I'm going to explain next how are we going to have these two relations over here, state 1 and state 2, in order to find the value of H2 and H1 in relations with your pressure. And also there's another term that we are going to use, which is your specific volume. Okay. Now, for further understanding on the analysis of the pump, you might want to go back to your textbook on chapter 5 and have a look at this 5.4, where you have the explanations on some steady flow energy and engineering devices, right? And the closest functions of pump is the same as the compressor. If you can read down here, it already explained the difference between pump and compressor. Alright, so let's moving on forward here. Okay, so when you are your missions is to find your thermal cycle efficiency, and that the mathematical expressions between W dot net and Q in, and that your W dot net here consists of work of your turbine minus work of your pump. And if you have a look at your diagram over here, your work pump is in between state 2 and state 1. Hence, when you are looking for your work pump, you can write it as work pump is equal to H2 minus your H1, right? The energy that you are looking for in your pump can be represented by H2 minus H1. Alright, and also there's another way to find your work pump. Okay, since we are trying to solve about your simple ideal Rankine cycle, which is a vapor and combined power cycle, right? So if you have a look at this 10.2 chapter, you will see that work pump can also be counted using your pressure difference, and also your specific volume. So we are going to write down here, okay, that your work pump can also be counted using specific volume, and your P2 minus your P1 is equal to H2 minus your H1. Okay, now let us make some checklist here, right? So we don't know what is V, right? And we do have P2, we do have P1, we don't know what is H2, and what about your H1? So if you have a look at here, your state 1 is actually in saturated liquid, right? And why is it in saturated liquid? Again, we go back to the functions of pump, right? For your pump to work, it has to be in fully liquid form. So going out from the turbine, you have some sort of some in vapor state, some in liquid state, until the condenser release all the heat, and now the steam becoming liquid, right? So for H1, you can directly read from table A5, and it is at fluid conditions over here. Okay, so we do have your H1, right? And then what about your V here? And why is it we don't write 2 or 1? Okay, again, we go back to the functions of pump. Basically, this pump is just to pump in your fluid from the condenser to the boiler, so the specific volume is the same, right? So we are going to make use V1, right? Because the informations that we have for V1 is much easier, right? Remember, if in order for you to read your property table, you will need two known value. So in this case, you already know that your pressure is 10 kilopascal, and even though you don't have directly the value of your enthalpy, but you do know that it can be read from HF. So let's have a look at here. So the pressure at state 1 is 10 kilopascal, and that you have your liquid condition, so you are going to consider this HF over here, right? Saturated liquid. So it's going to be 191.81, so you copy that one. And there's another crucial value that you will need is your specific volume, where your specific volume is actually your VF over here, and 10 kilopascal specific volume at saturated liquid, so this is the value over here. Alright, and please don't forget to write down the units of both enthalpy and specific volume. Okay, so how are we going to rewrite this one? So you are actually looking for your H2, right? What is the value of your H2 over here? So you are going to rewrite H2 is equal H1 plus with your specific volume at 1, P2 minus your P1. Alright, hence you plug in all the value that you already obtained above here inside this mathematical expressions. So you are going to have H2 is equal to this value over here. And I would like to remind you that please do not leave your units here, right? Please do not leave your units here. And for this kilopascal to be homogeneous, right, meaning that you are going to have homogeneous kilojoule per kg. Remember that kilopascal is also equal to kilonewton over meter squared. So you are going to cancel this meter squared with this m3, and finally the units will be equivalent to the units will be homogeneous with kilojoule per kilogram. And also you need to be careful when you make use of your scientific calculator to convert this value over here. So previously I have jotted down wrongly. This is not 1000 kilopascal, it should be 10,000 kilopascal, right? So please be careful when you make use of your scientific calculator. Alright, moving on to the next one, we would like to resolve state 3, and we already did so above here, okay, but what we don't have is your H3, okay. So given that your pressure and temperature, this is much easier. You can straight away look at your superheated table. So it's going to be table A6. We move into table A6. Yeah. So we are looking for 10 megapascal. Alright, there you go, down here. At 500 degrees C. So let's have a look at here. And what are we looking for? Previously, we are looking for your S3. Now we would like to have the H3. So H3 lies in this column over here. So at 10 megapascal for 500 degrees C, the value for your enthalpy is 3375. So let's have a look at this. We are trying to solve this question B, right? So by now, let's have some checklist. You already have H3, you already have H2 and H1, also H3 and H2. What about your H4 over here, right? So moving upwards, so your state 4 is this one, 10 kilopascal, and you know that S4, but you lack of one value, which is your H4, okay? Hence, this is why in the first part, it asks you to find the value of X4, because you are going to make use the general equations, which is Y is equal to YF plus XYFG. Now, previously you were looking for your, you make use of your S, now you are trying to look for your H4. So this is going to be HF at 4 plus with your X4 HFG at 4. Alright, so based on table A5, again because given to you pressure, okay, so we try to look for H4 is equal to HF4 plus X4 HFG4. So let's go to your table A5 over here, and at 10 kilopascal, what will be your HF? Okay, right, again it is 191.81, and what is your HFG? It is over here, so you copy that into your solutions. Alright, so now that you already have your all the value that you are going to need, right? So you can we can solve your thermal cycle efficiency over here. So when you plug in all the value that you already have, and finally you are going to get 40.2%, right? The thermal cycle efficiency is 40.2%. Alright, let's move to the last part of this question, where you need to find your m dot, or your mass flow rate of the steam. So how much is the mass flow rate going through this cycle, okay, the water inside this part. Alright, so let's have a look at that part. Alright, in the first sentence of these questions, you were given your W dot net, which is equal to 210 megawatt. Now, before you start to grow confused, right, I would like to stress out the difference between the work net here, that when you expand the mathematical expressions, it become like this, okay, and the work net that you have in here, right? So the difference between these two is that one you have the dot and this one you don't have the dot. Meaning that in order for this to become W dot, you will need this M dot. Okay, so W dot net is equal to M dot work of your turbine minus with work of your pump. Now, if you are going to use directly this W dot net over here 210 megawatt, you will need to change this one with Q dot in. Alright, I had just realized about this one. I have it wrong equations over here. It should be Q. I apologize about that. This should be Q. Sorry, Q small. Okay. So the unit should be inhomogeneous, right? Meaning if you are going to make use W net as 210 megawatt, the value over down here you need to have M dot times with this HQ minus H2, which is HQ minus H2. It's actually your Q in. Okay, so we don't have that. We don't have this M dot. In fact, in the C part, you were asked to find this M dot. That's why we are going to solve it state by state over here. I hope this confusion can clear your mind. What was the difference between W net with capital W and W net with small w. Okay, so if we are going to expand this W dot net, it is actually your W dot times with your work net is equal to 210 megawatt. And you already know that your work net is actually from this part up here, okay, H3 minus H4 minus H2 minus H1. So you can quickly have your work net over here, and you may rewrite this as M dot is equal to 210 megawatt, or if you want to leave it as kilos, all in kilos, so this is going to be 210,000 kilowatt divided by your work net value. So you have to take your calculator and calculate all this top part over here. Alright, so please again be careful with your unit over here. Alright, and because this one must be in kilogram per second, so if we expand this is actually your kilojoule per second. So when you cancel out this term, it's going to get the equivalent to this one. So finally, you will get your M dot is equal to 165 kilogram per second. Alright, with that we have completed the problem example that we have from this thermodynamics textbook, right? And this problem of steam power plant is actually under this subtopic, the ideal cycle. Okay, and also you will need to have some knowledge on mass energy of control volumes for you to understand further about your pump and your turbine. Okay, and finally you will also need to recap on how to read your property table for water. With that, we have finished this example. I will see you next how to solve your actual simple Rankine cycle. Thank you.